Good morning. Today is May 31st, last day of the May. We'll continue the electromagnetism. Today we are also going to talk about the electric flux. So last time we go over the fundamental definition of the electrical flux, which basically is the dot product of the electric field with the area. Today we're going to go over with a specific example. So what I'm drawing right now is a cube. Cube means every side is the exactly same length. Let's say it is the A. Let's say the electric field is the constant directions and the constant values, which is perpendicular to the surface. So if I call this surface 1, this is a surface 2, and then the back side is surface 3, this side 4, top is 5, bottom is 6. Okay, so let me give you an example. See, this is what I have right here. See, this is the face 1. This is another plane 2. The back side is 3, as you can tell. This is a 4, top is 5, the bottom is 6, okay? And then this chisel, we say that's the electric field. Okay, so that electric field, as you can tell, is perpendicular to the plane 1 and then plane 2. Okay? Now we need to do the calculations. So I put it right, no, that's too far away. I put it right here so you can still see it. And then we're going to calculate. Let's say first we want to calculate this part, right? The electric field passing through the plane 1. And then that specific electrical flux, we use the letter phi E1 represent this part. So based on the definition we went through yesterday, is E dot A. Again, that is equal to the magnitude of E times magnitude of A times cosine theta, where theta is the angle between the plane and the electric field, right? Just a quick review. So if we have a plane like that, this is our A, then the direction of the plane actually is the little normal vector perpendicular to the whole plane A. So in this case, if I use this guy, the little nail, to represent the direction of the plane 1, then that's the direction, right? Do you notice that? So the electric field and the plane, they form an angle theta. That theta actually from all the way from here to here. In other words, if I draw this, again, that would be, for plane 1, that would be, if this is our E, right? And this is the direction of the plane, then the angle between them is theta, where theta equal to 180 degrees. So that would be E times A times cosine 180 degrees. So cosine 180 degree actually equal to -1. So that would be negative E, which is the magnitude of the vector E, and then A, because this is the square, right? Each side is the letter A, so that's EA squared. Okay, so that's this guy. So what about the electrical flux for plane 2, which is this plane right here? Okay, and then that would be theta E2, again is E dot A, again is magnitude of E, magnitude of A, and then cosine theta. Again, the theta is the angle between the electrical field and the plane, the direction of plane 2, which is go to that direction. Since both point to the same direction, in other words, if this is the E, right, in the meantime, the direction of the plane B is also that. So the cosine theta actually is 0 degree. So it's magnitude of E, magnitude of A times cosine 0 degree. So that would be E dot A, since cosine 0 equal to 1. And then that would be E times A squared. Okay, now we look at the plane 3, which is this plane right here. Right? So the direction of the plane is that, and then the direction of E is that direction. So they form a 90 degree angle. So the third case, phi theta phi E3 equal to E dot A equal to magnitude of E times magnitude of A cosine theta, and then that is the magnitude of E times magnitude of A cosine 90 degree. So we know sine 90 degree is 1, but cosine 90 degree is 0, so that is 0. Now we need to look at the theta E4, which is this guy right here. See, that's 4. And then that equal to E dot A, again magnitude of E times magnitude of A, and then times cosine theta. So the angle of the plane 4 is that angle, the electric field, and the angle, plane 4, the former angle is also a 90 degree. So that would be E A times cosine 90 degree. Again, the whole thing equal to 0 because cosine 90 degree equal to 0. Now let's continue looking for E phi. Phi E5 would be E dot A. Again, it's magnitude of E times magnitude of A cosine theta. Now we need to figure out what exactly is the angle of theta in this case. So this is the plane number 5, right? So the direction of the plane is upwards, and then that's the direction of the electrical field. So they form a 90 degree angle. So that will be cosine 90 degree, again, that's 0. Now the last one is phi E6, which is the bottom, right? As you can imagine, the direction of the plane is go downwards, and then they form a 90 degree angles. So that is E dot A is magnitude of E times magnitude of A cosine theta, which is magnitude of E times magnitude A times cosine 90 degree, and then that equal to 0. Now we want to calculate the total electrical flux, which is VE1 plus VE2 plus VE3 plus VE4 plus VE5 plus VE6. And then VE1 is negative EA squared. VE2 is positive EA squared. And then the rest is just 0. So we plus 4 zeros. And then the whole thing is 0. So remember this result. That's going to be helpful when we study the Gaussians now. But right now, just keep that in mind. You know, if it's the closed cube, if you try to find the total electrical flux, actually it turns out to be 0. And I think that's probably it. Now I would like to share with you today, but next time what I try to do is the following. Because today we're doing the electric field is perpendicular to the face, right? Next time I'm going to talk a little bit like that. Okay, so we form an angle. So in that case, how do we calculate the electrical flux of each plane, and what was the total plane of the electrical flux? With that being said, thank you again for watching the video. Please leave in the comment area if you have any questions. Thank you. Bye-bye.